Hello everyone, my name is Li Bingxia and I come from the Department of Mathematics in Xiamen University, Malaysia. Today I'm going to present one of the most fundamental concepts in mathematical analysis, namely open balls, together with an important theorem about open balls and its proof. This topic is important because many concepts that we learn in single variable calculus, such as limits and continuity, are built upon the idea of points being close to one another. Open balls provide the mathematical language for describing this idea precisely. So I would like to introduce Firstly, I will introduce the introduction and background of open ball. Next, I will talk about the definition of open ball, which consists of the geometric interpretation and basic property, with example of an open ball. The third one is a main theorem of open ball and open sets and its proof. Finally, I will talk about the applications of open ball. So before studying the theorem, let us first understand what an open ball is. In everyday life, we often say that two points are near each other. However, mathematics requires a precise definition of what near means. An open ball is exactly such a definition. It represents all points whose distance from the fixed center is smaller than a given radius. Although the definition looks simple, it is one of the foundations of mathematical analysis and topology. It allows us to define open sets continuity, limits convergence, and many other important concepts. To define an open ball, we first need the idea of distance. In Euclidean space, we measure distance using the Euclidean norm. For a point x equals to x1 dot x2 and so on to xn, its norm measures its length from the origin. Using this norm, the distance between 2 points x and y is simply the norm of their difference. One important property of this distance is the triangle inequality. The triangle inequality tells us the direct distance from one point to another is never greater than traveling through an intermediate point. This property may seem obvious geometrically, but it is actually the key idea behind today's proof. Please keep the triangle inequality in mind because we will use it shortly. So now let us define an open ball. Suppose we have a center point x0 and a positive number r called the radius. The open ball center at x0 with radius r is the set of all points whose distance from x0 is strictly less than r. Notice the word strictly, since the distance must be less than the radius. Points exactly on the boundary are not included. This is why we call it an open ball. The figure on this slide illustrates this idea. Every point inside the circle belongs to the open ball, while the boundary itself does not. So the meaning of an open ball depends on the dimension. In one dimension, an open ball is simply an open interval. For example, the open ball center at A with radius r is the interval from a minus r to a plus r, excluding the endpoints. In two dimensions, the open ball becomes the interior of a circle. In three dimensions, it becomes the interior of a sphere. So an open ball contains all interior points but not the boundary. It's really a higher dimensional generalization of familiar geometric objects. Another simple property is that if we increase the radius, the open ball becomes larger. Therefore, every smaller open ball is contained inside a larger one with the same center. A larger radius always produces a larger open ball, as I give here the ball center at x0 with the radius r1 is contained in the ball center at x0 with radius r2, which we have given that r1 is smaller or equal to r2. So let us look at a concrete example. Consider the open ball center at the point 1.2 with radius 3. This consists of all points whose distance from the center is less than 3. Now let us check whether the point P equals to 2.3 belongs to this open ball. Using the distance formula, we calculate that the distance from P to the center is the square root of 2. Since the square root of 2 is approximately 1.41, which is less than 3, the point lies inside the open ball. This example shows how we determine whether a point belongs to an open ball by comparing its distance with the radius. Now we come to the main theorem of this presentation. The theorem states, suppose x1 is already inside an open ball center at x0, then we can always find another smaller open ball center at x1 that is completely contained inside the original open ball. Let us first understand the meaning of this theorem before proving it. Imagine that you are standing somewhere inside a room, but not touching the walls. No matter where you stand, there is always a small circle around you that stays entirely inside the room. The theorem says that an open ball behaves exactly like this. Every interior point has its own little safe region that never reaches the boundary. This idea is actually one of the defining properties of an open set. Now let us prove the theorem. Suppose we choose any point x inside the smaller open ball center at x1. By the definition of an open ball, the distance from x to x1 is smaller than the smaller radius. The radius was carefully chosen so that when we add it to the distance from x1 to the original center, x0, the total is still less than the original radius. Now we apply the triangle inequality. The distance from x directly to the original center, x0, cannot exceed the distance from x to x1 plus the distance from x1 to x0. Since this sum is already less than the original radius, the distance from x to x0 must also be less than the original radius. Therefore, the point x belongs to the original open ball. Because every point inside the smaller ball satisfies this property, we conclude that the entire smaller open ball is contained inside the larger one. So this completes the proof. The key idea behind this proof is actually very simple. Instead of measuring the distance directly from x to the original center, we go for the intermediate point x1. The triangle inequality guarantees that this direct path is long enough to control the direct distance. This is why the triangle inequality is the central tool in the proof. So why is this theorem important? The theorem tells us that every point inside an open ball has some breathing space. In other words, interior points are not close to the boundary. This seemingly simple property forms to the basis of the definition of an open set. It is also essential when studying continuity. In calculus, we say that a function is continuous if points that are sufficiently close to the input are mapped to points that remain close to the output. Open balls provide the precise mathematical language for expressing this idea. The same concept also appears in limits, convergence, metric spaces, topology, and many advanced areas of mathematics. Therefore, today's theorem looks elementary. It is one of the building blocks of a modern analysis. To conclude, we introduce the concept of an open ball, discuss its geometric meaning, work through an example, prove an important theorem, and explain why the theorem is fundamental in mathematical analysis. So, this property is exactly what makes open balls and open sets so useful throughout calculus and analysis. The most important takeaway is that every point inside an open ball has its own smaller open ball that remains entirely inside the original one. So thank you very much for your attention. That's all of my presentation.